Hello and welcome to the session where we are going to continue with the development of case studies in developing an overall generalized framework for our mass balances and material balances that describe concentration as it varies both in time and space. So in this case study, we are now considering flow through a cylindrical tube, much like we did last time. And again, we are fed with a component with the stream with the concentration of Ca in for some component. In this case, the walls of the tube are permeable, and that means that our component A is diffusing out across the walls of the tube as well. So that's new, right? In contrast to the previous case, which only had flow through the tube and diffusion across the tube, that was all happening axially only. Now we have that the component can also diffuse out across the walls of the tube as well. And if that's the case, then we can no longer assume that there's no radial flux, right? If component A is leaving on the walls of this tube, then there is a bulk movement towards the wall of the tube, and that means there is going to be a concentration gradient in the radial direction as well. The axial difference still exists. So axially, the concentration is still varying, but now the concentration is also varying radially. To understand this a little better, let's go back to the control volume that we drew earlier. So we had defined our control volume between the points Z and Z plus delta Z, and that was simply two cross sections in the tube, and the space between those cross sections was the space of interest. Now in this space, we can easily imagine that if our component is diffusing across the walls of this tube, then locally close by the wall we will have an immediate low concentration of the component in comparison with the concentration in the center line. So in the center line, we have our component being fed continuously, and we have component A that's leaving the tube through the walls. So we can imagine that because component A is leaving here, that's going to deplete component A near the wall. So we'll have a low concentration near the wall, and then that's going to drive diffusion towards the wall. Remember, we diffuse from high concentrations to low, so there'll be a net flux of component A towards the wall. And as long as that concentration difference exists, then we have to concern ourselves with a flux that's in the R direction together with a flux that's in the Z direction. And now we can imagine that as the fluid flows along, that component A is continuously leaving the space. So A is diffusing away from the center of the fluid, and so as we consider points further down the tube, we will have a progressively reducing concentration of component A. So A is reducing in the axial direction because A is also leaving in the radial direction. So if we think of a fluid element that enters, let's imagine there's a small packet of fluid that has entered, and then let's say the fluid just enters here and then it's spread out radially, and then that same group of fluid elements or molecules moves in the next time instant to this position. Then some of A will leave from that group, and then as that same group moves deeper in, more of A will have left, and so as that plug of fluid elements keeps traveling down the tube, it's losing more and more of component A. And so if we were to track how that concentration is varying axially, we can see that concentration of component A is dropping axially. And so we have a variation in the axial direction as well as in the radial direction. And so this picture that we drew earlier is no longer sufficient to describe this situation. And that's because we now have concentration varying in the R direction. Remember, this picture was what we could draw if we assumed that there was no radial direction or radial variation. So now we have to acknowledge that the concentration is a function of time, axial position, and radial position. And remember what we said. So in terms of a useful approach to solving problems of this nature, we start out with a sketch, and then we consider all kinds of variations. So we can see that, of course, the concentration is going to vary in Z. Now we've said it's varying in R as well. So to incorporate the radial transfer, we will partition the space in the R direction. So when we said we had an axial variation, we chose a position Z and we chose a small distance Z plus delta Z. So now for the radial direction, let's choose a position R and choose a small direction R plus delta R. And so if we zoom in on that control element that we drew earlier, right, so here I'm trying to show that we zoom in. Now if we look on the face, on this area face of this tube, we can select a position R, and then we can select a position R plus delta R. So now we are partitioning our space in R and in Z. So if we think now about the shape of the object that we are talking about, it's this annular space, right? You can imagine this as a pipeline, so as a short pipeline. So the pipeline's length is delta Z, and that pipeline also has a thickness delta R. So the thickness of the pipeline is delta R. It has an inner diameter of R and an outer diameter of R plus delta R. And now we've described it as a pipeline, but actually the flow is in through the thickness of this pipeline. So our control volume is not the interior of the space. Our control volume is actually through the thickness of this pipe. So here we are imagining that as our fluid flows through the system, that it's going to enter this annular space. And of course, this is not a real pipeline. It's not as if there is an actual wall inside of this tube. This is our selection of a space. So we are simply defining a position R and a position R plus delta R. In the same way that we arbitrarily chose axial position Z and Z plus delta Z, we've chosen R and R plus delta R. So we are choosing to look at a specific sub-volume here. And this time the sub-volume is in this space. So it's in this, in this thickness of this imaginary tube. So we have an imaginary tube that's sitting inside of our pipeline. And that imaginary tube has a thickness delta R. And we are writing a balance on the thickness of this tube. And the reason that we've chosen such a strange space is because this is the space that is giving us the dimensional change of interest. So it's giving us, number one, it's giving us the axial difference, so Z to Z plus delta Z. So the two faces of this imaginary tube are at Z and Z plus delta Z. And then also in terms of the radial position, it's giving us the space between R and R plus delta R. So we have in effect identified that those are the two dimensions of interest, Z and R. And if we want to write a material balance which respects that there are differences in Z and R, then we need to create volumes that are within those kinds of bounds. So we need to consider small changes in these two dimensions. And so when we just think about what those kinds of spaces imply, what they mean, when we put that together, it turns out that the shape is like so. So it's not the case that we've chosen a volume like this, right? The better way to see this is that we've decided or we've identified that our variation is in these two dimensions. And so for us to consider a change across those two dimensions, we recognize that this is the type of shape that results. So it's something to spend a bit of time on. It's something to spend some time imagining and understanding how the shape results. And the best way to do that is by progression with the previous case study. So in the previous case study, we understood how our space was between z and z plus delta z. And when we chose the space like that, we were able to write a material balance and develop our concentration as a function of z, and even with time, so we even solved the equations. So it's just one step beyond that now. We are just going one dimension higher. We are acknowledging that the concentration varies in an additional dimension now, and so that additional dimension is also radially. And so to accomplish radial variation as well, we need to select R and R plus delta R. Right, and now that we've done this, now that we've chosen our control volume, we can go ahead and estimate the usual things. So our usual process is, we usually just start talking about the number of moles in the space. So we write the concentration in the space, and we multiply that by the volume of the space. In this case, the volume estimate is a little bit more complicated. So here we estimate the volume by first taking the inside perimeter. So of course the length of the perimeter of a circle is 2 pi r. So that's this inside perimeter. And then if we multiply it by delta r, then that's an approximation to the area out here, this dark red shaded area. So 2 pi r times delta r is an estimate of this area. And then if we multiply that by delta z, then that's going to estimate for us the volume of this entire annular space. So 2 pi r delta z, that's an estimate of the volume of that space. So delta V times the concentration is the number of moles in that annulus. Right, so again, it's the thickness of this pipeline, this imaginary pipeline, that's the control volume, and so the number of moles in this space, that's what we are trying to estimate here. And then we have flux. Now we have to consider flux, and again, flux is in 2 dimensions, right? Number one, as we said, we expect the concentration to vary down the pipeline, but also because the component is diffusing out, is permeating through the walls and diffusing away from the tube, then we also have a flux in the R direction. So we've got flux in the Z direction and flux in the R dimension. And so we can acknowledge now that the flux is a vector in both Z and R. So we can sketch that here. So if we add little wavy arrows to denote fluxes, you can see a flux in the Z direction and flux in the R dimension. And we can then write expressions for the flux. So we know that the flux is actually a vector, and it's a vector of 2 dimensions. So we can unpack that and write expressions for the flux in each dimension. So for flux in the Z direction, and this is something we've already developed before, we wrote that the flux was equal to the diffusion flux plus the convection flux. And in fact here we might want to specify that this is the velocity in the Z direction. So that's 1 dimension taken care of. And now we can think about the flux in the R direction as well. So in the R direction, we only have diffusion, right? There's no bulk movement in the R direction, right? That's of course in contrast with the Z direction. So in the Z direction, the fluid is flowing. We can talk about a velocity of the fluid, of the bulk fluid as it flows through. We can't really talk about a bulk velocity of the fluid in the R direction. There's no UR to concern ourselves with here. So in terms of the R dimension, we only have diffusion. right? So because A is diffusing across the walls here, then we have a local low concentration here and a high concentration there. So A is diffusing in the radial direction. So we can say simply that the flux for R is has this expression. So it's the same form, it's the same diffusivity, because it's the same molecules. So component A is diffusing against some solute or something like that. So it's the same diffusivity, and it's the same variable. It's also concentration, but the dimension is different. So instead of considering changes in Z, we are considering changes in R. Right, so it's this exact same form of equation that we are used to for estimating the diffusion flux. And now, when we want to write our material balance, of course, the next step is to write down the rate of change of the number of moles in the space. And there we would typically multiply the flux in one direction by the area that's normal to it. So we've done it before for the case of the pipeline. So we said flux in the Z direction, we would multiply by the area normal to that. Now this time the area normal to the flux in the Z direction is this reddish is this bright red surface, and we estimate the area of the surface, as we said just now, by 2 pi r times delta r. So we can say here the area that's normal to the Z flux is given by, and we call it AZ just to mean the area that is normal to the Z direction. So it's 2 pi r delta r. And then for flux in the R direction, that flux is actually the inside of the tube of this imaginary annulus. So as component A diffuses from the center towards the walls, it's going to cross this surface. So if you like, A is diffusing, is radiating its way outwards from the center here. And so the first surface it sees is this inside surface here. And if you think of it, you've got the perimeter here, 2 pi r, and then the length there, delta z. So the inside surface of this annulus is 2 pi r delta z, right? And in fact here, we do in and out. So in the z direction, we have the flux in at the surface here and then out at that surface there. And this surface is the same surface as this. The area here is the same as the area here. Now, when we look in the r direction, the inside area is not the same as the outside area, right? The outside area is at 2 pi r, is at r plus delta r. That's the radius there. So the area on the outside of this annulus is going to be 2 pi times r plus dr and then times delta z. So the area at r plus delta r is 2 pi r plus delta r times delta z. So the area is a little more complicated now, but we'll see there's a nice neat way that we'll come up with to handle that also. Okay, so that's defining all the quantities for us. Hopefully now we understand the physical picture, and it may be worth your time to pause the video and spend some time just sketching out the situation. Just imagine if you knew that the concentration was varying in these two dimensions, what kind of control volume could you come up with? And spend some time trying to do that. Maybe just try to forget everything we've said now and try to create some volume that you could use to balance over yourself. And hopefully you'll find that it does come to the same kind of volume that we are seeing here. So try to imagine creating a control volume which was varying in Z and Z plus delta Z, and also was varying in R plus delta R, and hopefully you'll see that that this is the only possible shape for that. So pause the video now and spend some time just trying to figure that out. Then also spend some time trying to capture the number of moles in that space. So if we have concluded this is the right type of subvolume, then estimate the number of moles in that subvolume, and you should come to that amount. And then, quite importantly, sketch out the fluxes that you have across the space, and then write down the molar fluxes at each surface here. So there's a flat surface here for flux in the z directions. There's a curved surface on the inside for a radial flux, and there's a curved surface on for the outside here. That's also for radial flux. So be sure that each element here is properly understood, both in terms of discovering what the flux is and in terms of what the areas are. All right, now if all that's well enough established, and again, please do pause the video and get this as right as you can. So if you can get this right for this situation, the rest of the course is pretty much sorted, right? This is probably one of the more sophisticated case studies that we'll cover. And so if you can understand unsteady state two-dimensional flux, the rest are merely variants on this type of problem. All right, so we can write our overall material balance here. We can say the rate of change of moles in this weird little space will equal the rate at which component A is entering the space. So you have the flux in the z direction at position z. So we multiply by the area normal to that z. And then we look at the flux out of the space. So we look at the rightmost face, and then the flux going out there times that area. So that's all the flux in the z direction. And then we also have flux in the r direction. So we enter the space, right? The flux here is actually entering into our annulus. So remember, we are basically not including the volume on the inside of this annulus. That doesn't count in terms of our space. So if we have flux from the inside reaching that annulus, then that is a contribution to our space there. So that's entering into our space, and then leaving the space is here. So on the outer surface here, flux in this direction is a loss of moles from that space. Right, so those are all the fluxes and areas, and that's the sum of all that gives us the rate of change of moles in the space. And then we can go ahead and substitute all the definitions that we've developed. So for the number of moles there, concentration times the volume of the space, and then we can substitute for each of the fluxes. So we know in the z direction you have convection and diffusion, and so you can see the flux in the z direction at position z and at z plus delta z, and then multiplied by the area of those faces as well. And then the same thing in the radial direction. Right, so again, pause the video, spend some time checking that you agree with the translation from here to here. Now, let's look at this equation for a bit. Let's try and anticipate what we are going to do to this equation next. You may have noticed the pattern so far that we usually divide out by the geometric side of this. So we would try to divide by 2 pi r delta z, and you can see 2 pi r in most places. So we can see for these two terms, 2 pi r delta r at least is going to cancel. We can see there's going to be a delta z left over. So, and we can imagine we'll get a ddz out of that. So these first two terms, we can sort of see what's going to happen. For these next two terms, you can see here we've got the 2 pi r that can cancel with that. But here we've got 2 pi r plus delta r. Remember that outer surface is slightly bigger. So we can't cancel this r plus delta r by this r. So we can imagine there's a bit of inconvenience coming up here. And the way around this is to generalize our concept of this area. So we can go ahead and write this. This is correct, right? There's nothing wrong with writing the area in this way, or the circumference in this way, 2 pi r and 2 pi r plus delta r. But we could write it a little more generally if we say the area that's normal to the radial direction. So that's 2 pi r delta z at r, so where r equals r. Right? It sounds like a silly thing to say for this one. But when we write the area at r plus delta r, here we could write this as 2 pi r delta z at r equals r plus delta r. So see here, we've now managed to write the area in terms of the same function. Right? We are basically saying, consider this thing to be our area function, and it's just the case that we evaluate that area at two different radial positions, right? And it's just a definition. It looks like it's just notation. It's a bit of progress in terms of notation, but that is important. Let's see how that helps things. So this is the same picture, nothing new there. So now what we can do with this definition is, instead of multiplying this 2 pi r delta z out here, let's bring it in here. So remember these square brackets, that's evaluated at r, and this is evaluated at r plus delta r. So if we bring this this factor in here, you can see we can replace this by 2 pi r delta z, and it's just that r is evaluated at r plus delta r. So our equation can now be written like this, right? We brought those terms in, and now we can see we've got the same form here. And then let's go ahead and divide both sides by 2 pi r delta z. So clearly the left-hand side, that simply cancels. For the first two terms, as we said, the 2 pi r delta r can cancel nicely. And so this function will simply be divided by delta z. And you can see it's the same function in each case, and then evaluated at z and evaluated at z plus delta z. And then clearly we are going to look for taking the limit as delta z goes to 0. So we would have here ddz of this function. Right, so that's the first two terms. And then for the second two terms, dividing through by 2 pi r delta z, we still can't cancel this r here, right? This r is it's evaluated at r, whereas this r is evaluated at r plus delta r. So we can't cancel the r here, so we won't try to. We can't, so we can't even try to. Anyway, so we can go and divide by 2 pi delta z at least, right? The delta z is going to be the same in both cases, right? And to see that, just remember, inside the tube, if you look along the length, that's the same delta z as you get on the outside of the tube. Delta z inside the tube and outside the tube, it's the same delta z. So delta z is not changing, so that can cancel, and then the 2 pi's can also cancel. And then we are left with an r in here, and we couldn't cancel the r, so we divided by 2 pi r delta z everywhere. So we have to retain the 1 over r here. And so our function now is going to be minus dae dc dr, and then r. So minus dae dc dr times r. So that's the function in this case. And then here we have 2 pi r delta z. We don't have a delta r, so the delta r goes here. So we've talked about this one up here. Down here we can see, as we let delta r go to 0, if we take the limit delta r going to 0, then you've got a function evaluated at r and the same function evaluated at r plus delta r. So this is also going to give us a ddr of this function. So if you do all that, you are going to get ddz of this function here, and then plus 1 over r times ddr of this function. So that's there. Okay, and we're close to done. We can expand this out if we want to, right? So you could say, well, I'm taking dAe as a constant, so I'm not concerned about gradients in this. So if I differentiate with respect to z, this is simply going to be dAe dc, d2ca dz squared. So that's there. And then we have this other term in here as well, so we need ddz of ca times u. So we can leave it like this, or we, if we are not assuming u is changing with z, then you can take the u out as a constant also. So that's there. And then if you we can see two functions in R on the inside here. So this is a function in R, and then R is kind of a trivial function in R also. So it's a product of two functions in R. So if you take ddr, you can expand this. So if you leave the first one and differentiate this one, then you get r d2ca dr squared. I see I've missed my dAe, so I'm just going to take out a dAe here, d sub ae. Right, so that's one derivative, and then you can differentiate the r here, and you get dAe dca dr. But anyway, all this is quite unnecessary. You don't really have to expand on these derivatives in this way. So here the r's can cancel, leaving you with that. Here it's not going to cancel, so you carry the 1 over r. So anyway, however you choose to finally represent your PDE, you will have a first order term in time, and you can see it's going to be second order in terms of the axial position z, and it's also second order in terms of the radial position r. Right, so if you count it up, that means we need 5 boundary conditions to solve this problem. And we will have a separate section, a separate lecture on just boundary conditions. So it's an important enough topic that we'll do a separate lecture on that. For now, let's just appreciate that our concentration is going to vary in time, axial position, and radial position. So there's a lot going on in this tube, even though it's just convection and just diffusion. And something for us perhaps to think about is that, you see all these steps, it's really quite a lot of detailed and rigorous thinking, and in fact some of us enjoy this. I mean, it does grow on you. You do quite enjoy doing this, but at some stage you realize you can't keep doing this, and it starts to seem like there is a kind of pattern that's emerging here, and we would like to think about generalizing this. Is there not some better way of starting to develop these material balances?